Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Energy Unleashed: The Power and Secrets of Thermodynamics. The laws of thermodynamics stand as some of the most fundamental principles in physics, describing the relationships between energy, heat, and work. These laws underpin countless natural processes and technological advancements, shaping our understanding of the universe's structure and behavior. To truly appreciate the significance of these principles, it is essential to delve into their historical development, explore their foundational concepts, and examine their wide-ranging applications. The history of thermodynamics is rooted in the Industrial Revolution, a period of rapid technological progress that spurred the need to understand and optimize heat engines. In the late 18th and early 19th centuries, inventors and scientists began systematically investigating the principles governing heat and work. The French physicist Sadi Carnot, often considered the father of thermodynamics, made pioneering contributions in his 1824 work Reflections on the Motive Power of Fire. Carnot introduced the concept of a theoretical heat engine operating at maximum efficiency, laying the groundwork for the second law of thermodynamics. His insights, though rooted in practical engineering, became a cornerstone for the scientific exploration of energy transformations. Building on Carnot's ideas, the mid-19th century saw significant advancements from luminaries such as Rudolf Clausius, William Thomson, later Lord Kelvin, and James Prescott Joule. Clausius formalized the second law of thermodynamics, introducing the concept of entropy to describe the tendency of energy to disperse and systems to evolve toward disorder. Joule's meticulous experiments established the equivalence of heat and work, providing the empirical foundation for the first law of thermodynamics, the principle of energy conservation. Together, these developments framed a comprehensive understanding of energy systems, connecting microscopic molecular behaviors with macroscopic phenomena. The first law of thermodynamics, often summarized as energy cannot be created or destroyed, is a direct expression of energy conservation. It states that the total energy of an isolated system remains constant, though it can transform from one form to another, such as from thermal energy to mechanical work. Consider a simple steam engine as an example. Heat generated by burning fuel is transferred to water, producing steam that drives a piston. In this process, the chemical energy stored in the fuel is converted into thermal energy, then into mechanical work. This principle underlies countless technologies, from car engines to power plants, and ensures that energy accounting remains consistent across all physical processes. The second law of thermodynamics introduces the concept of irreversibility in natural processes and the inexorable increase of entropy in isolated systems. It asserts that heat naturally flows from regions of higher temperature to lower temperature and that energy conversions are never perfectly efficient. For example, when boiling water on a stovetop, heat flows from the burner, high temperature, into the water, lower temperature, raising its temperature. However, some of this heat is inevitably lost to the surrounding air, illustrating the inefficiencies dictated by the second law. This principle has profound implications, from understanding the limits of engine efficiency to explaining the arrow of time in the universe. The historical development of thermodynamics culminated in the late 19th and early 20th centuries with the formulation of the third law and the integration of thermodynamic principles into broader scientific frameworks. Walther Nernst, a German chemist, articulated the third law, which states that as a system approaches absolute zero, the entropy of the system approaches a constant minimum. This principle plays a crucial role in low-temperature physics, influencing fields like cryogenics and quantum mechanics. Applications of thermodynamics are as vast as its foundational principles. In industry, thermodynamic laws govern the design and operation of engines, turbines, refrigerators, and heat exchangers. For example, air conditioning systems rely on the principles of heat transfer and the thermodynamic cycle to cool spaces efficiently. In natural sciences, thermodynamics provides critical insights into chemical reactions, phase changes, and biological processes. The human body, for instance, can be understood as a thermodynamic system that converts chemical energy from food into mechanical work and heat, maintaining life functions. Beyond terrestrial applications, thermodynamics has extended its reach to the cosmos. The study of stellar processes, black holes, and the evolution of the universe relies heavily on thermodynamic principles. The life cycle of stars, from their formation to eventual collapse, is governed by the balance of thermal pressure and gravitational forces, a direct application of the laws of thermodynamics. These principles also underpin cutting-edge technologies like renewable energy systems and energy storage solutions, highlighting their enduring relevance in addressing modern challenges. Building upon the foundational principles outlined in the first part, the intricate workings of the laws of thermodynamics reveal their profound impact on both the natural world and human-engineered systems. These laws, which encapsulate energy conservation, entropy, and the behavior of systems in equilibrium, are expressed through elegant mathematical formulations that guide scientists and engineers in solving complex problems and advancing technology. The first law of thermodynamics essentially states that energy within a closed system is conserved. In other words, energy cannot be created or destroyed, it can only be transformed from one form to another. This is most commonly applied in the analysis of heat engines. For example, in an engine, fuel is burned to produce heat, which in turn increases the system's internal energy. Some of this heat energy is used to do mechanical work, such as moving a piston, while the rest is lost as waste heat to the surroundings. Understanding this process is critical to optimizing engine efficiency, ensuring that the maximum possible energy is converted into useful work, rather than wasted as heat. To further illustrate, consider the example of a steam engine. Heat is added to the system, raising the internal energy of the water until it turns into steam. This steam then drives a piston, which performs work. However, some of the energy is inevitably lost as heat to the environment. The first law allows us to track and quantify how much energy enters and exits the system, ensuring that energy conservation is accounted for at every stage. The second law of thermodynamics introduces a critical concept, entropy, which can be understood as a measure of disorder or randomness within a system. The second law asserts that in any energy transfer or transformation, the total entropy of an isolated system will either increase or remain the same, it never decreases. This law essentially explains why certain processes are irreversible, such as why heat naturally flows from hot objects to cold ones, or why an ice cube melts in warm water but will not spontaneously freeze back. The second law has profound implications for the efficiency of energy systems. It means that no process can be 100% efficient because some energy will always be lost to disorder. This is evident in the operation of heat engines, which can never convert all the heat they generate into useful work. Instead, part of the energy is inevitably lost as heat to the surroundings, increasing the system's entropy. This inevitable increase in entropy explains why certain processes, like mixing hot and cold water, or burning fuel, move in one direction and cannot spontaneously reverse themselves. Another key feature of the second law is that it explains why time flows in one direction, the arrow of time. As entropy increases, systems move toward a state of greater disorder, and this progression is irreversible. This concept also plays a crucial role in understanding the thermodynamics of biological systems, where living organisms constantly work to maintain a state of low entropy within their bodies while generating waste heat and increasing the entropy of their surroundings. The third law of thermodynamics complements these first two laws by describing what happens to entropy as a system approaches absolute zero, the theoretical temperature at which all molecular motion stops. As the temperature of a system decreases, its entropy also decreases, and at absolute zero, the system's entropy approaches a minimum value. While reaching absolute zero is practically impossible, this law is fundamental in fields such as cryogenics, where scientists work with very low temperatures. At these extremely low temperatures, the entropy of the system is minimized, and the system's properties can be studied in states of almost perfect order. The third law has practical implications in understanding the behavior of materials at ultra-low temperatures, such as superconductors, which exhibit zero electrical resistance at near-zero temperatures. It also informs the development of quantum technologies and helps researchers design systems that can achieve very specific energy states with minimal entropy. Thermodynamics also finds extensive application in many modern technological advancements. For instance, refrigerators and air conditioners operate on principles derived from the second law. They transfer heat from a cool space, inside the fridge or room, to a warmer space, outside, using mechanical work to drive the process. Although the system works by moving heat against its natural flow, from cold to hot, the process still increases the overall entropy of the surroundings, ensuring compliance with the second law. In the field of chemistry, thermodynamics helps us understand how chemical reactions proceed. In particular, the concept of Gibbs free energy, which combines the first and second laws, tells us whether a chemical reaction will occur spontaneously. If a reaction results in a decrease in free energy and an increase in entropy, it will proceed without external intervention. This principle governs processes like combustion and the formation of chemical bonds, allowing chemists to predict the behavior of molecules in various conditions. In the biological world, living organisms are essentially thermodynamic systems. They must maintain a low entropy state internally, which they achieve by consuming energy from food, sunlight, or other sources, and expelling waste in the form of heat and molecules. This constant influx and outflux of energy is essential for life processes such as metabolism, growth, and reproduction. Organisms are constantly fighting entropy by maintaining order within their cells and tissues, but in doing so, they increase the entropy of their environment. Finally, in astrophysics, thermodynamic principles govern the life cycle of stars, black holes, and even the fate of the universe. Stars, for example, are giant thermodynamic engines, converting nuclear energy into heat and light through nuclear fusion. The second law is essential in understanding the evolution of these stars, from their birth in nebulae to their eventual death as white dwarfs, neutron stars, or black holes. The increasing entropy of a star as it burns through its fuel leads to its eventual collapse and transformation into a less ordered state. As we move into the final part of our exploration of the laws of thermodynamics, it becomes clear that these principles extend far beyond the theoretical. They permeate diverse fields of science and technology, influencing everything from the smallest quantum systems to the vast expanses of the universe. The application of thermodynamics is not limited to traditional engineering or chemistry. It plays a central role in emerging technologies and the quest to solve some of humanity's greatest challenges. In the field of quantum mechanics, thermodynamic principles are essential for understanding how energy behaves at microscopic scales. One of the most intriguing developments in recent years has been the rise of quantum thermodynamics, which combines the principles of quantum mechanics with classical thermodynamics. Unlike classical systems, which operate with predictable energy states, quantum systems exhibit probabilistic behavior, where energy levels can exist in superposition, simultaneously in multiple states until measured. For example, quantum computers, which use qubits instead of classical bits, depend on the principles of quantum thermodynamics to function. They perform complex calculations by exploiting quantum states, potentially solving problems that would be impossible for classical computers to handle. However, quantum systems are inherently subject to entropy in ways that classical systems are not. Quantum coherence, the ability of qubits to maintain their quantum states for long periods, is highly sensitive to changes in entropy. This relationship makes thermodynamics crucial for developing efficient quantum computers and understanding how to control and mitigate quantum decoherence. The intersection of thermodynamics and nanotechnology is another exciting frontier. Nanomaterials, materials engineered at the atomic or molecular scale, often exhibit unique properties that differ from those of bulk materials. These differences can arise due to quantum effects or changes in entropy at small scales. In nanotechnology, controlling energy flows and minimizing energy loss is vital for designing more efficient energy storage devices, transistors, and sensors. Nanostructures can also be used to improve heat dissipation in electronics, an application critical for the development of faster and more energy-efficient devices. One of the most significant modern applications of thermodynamics is in the development of renewable energy technologies. As the world faces the realities of climate change and dwindling fossil fuel reserves, there is a growing need for sustainable, clean sources of energy. Thermodynamics provides the foundational understanding for designing systems that harness natural energy efficiently. Solar panels, wind turbines, geothermal plants, and hydroelectric dams all rely on thermodynamic principles to convert natural energy sources into usable power. For instance, solar energy is captured through photovoltaic cells, which convert sunlight directly into electricity. This process involves the absorption of photons by the solar panels, which then create electron flows. Understanding the thermodynamics of how energy from sunlight can be most efficiently converted into electrical power is crucial for improving the efficiency of these systems. Advances in solar thermal energy, where sunlight is concentrated to heat water or air, also rely on thermodynamic principles to optimize heat transfer and minimize energy losses. Wind energy, another popular renewable resource, works through turbines that convert the kinetic energy of wind into mechanical energy, which is then transformed into electricity. The efficiency of wind turbines depends on the principles of energy conservation and the laws of entropy. Wind turbines must operate in conditions where they extract as much energy from the wind as possible while minimizing friction and heat loss to the surrounding environment. The role of thermodynamics extends into the realm of energy storage as well. The efficient storage and retrieval of energy are critical for ensuring the viability of renewable energy sources, which can be intermittent. Batteries, supercapacitors, and other storage technologies depend on thermodynamic principles to manage energy efficiently. For example, the operation of a lithium-ion battery relies on the movement of lithium ions between the anode and cathode, a process governed by electrochemical thermodynamics. Research into new storage methods, such as solid-state batteries, is also focused on improving efficiency and minimizing losses, all while adhering to the fundamental laws of thermodynamics. In the realm of cosmology, thermodynamics continues to provide profound insights into the structure and evolution of the universe. One of the most significant implications of thermodynamics is the concept of the heat death of the universe, a scenario where the universe has reached a state of maximum entropy. In this state, all available energy would be evenly spread out, and no further work could be performed. This theory, grounded in the second law of thermodynamics, suggests that over an unimaginable timescale, all stars will burn out, black holes will evaporate, and the universe will become a cold, dark expanse. However, thermodynamics also plays a key role in understanding the Big Bang and the early stages of the universe. During the early moments after the Big Bang, the universe was in a highly ordered, hot state. As the universe expanded, entropy increased, and energy became more evenly distributed, setting the stage for the formation of galaxies, stars, and eventually, planets. The study of cosmic microwave background radiation and the thermodynamic properties of black holes helps physicists understand the universe's past and its eventual fate. In biological systems, thermodynamics remains integral to understanding life itself. The processes of metabolism, cellular respiration, and energy transfer are all governed by the laws of thermodynamics. Living organisms continuously extract energy from their surroundings, whether through food or sunlight, and use it to maintain order within their bodies, fighting against the natural tendency toward entropy. For example, in cellular respiration, glucose molecules are broken down in the presence of oxygen, releasing energy that the cell uses to maintain its functions. This process follows the first law of thermodynamics, as the chemical energy stored in glucose is transformed into usable energy for the cell while heat is released as a byproduct. The study of thermodynamics in life sciences is expanding into areas like synthetic biology, where scientists are attempting to engineer lifelike processes, and bioengineering, which seeks to harness biological systems for energy production and medical applications. Innovations such as biofuels and the design of energy-efficient systems based on biological processes rely on thermodynamic principles to ensure that they are both sustainable and effective. As we look to the future, the implications of thermodynamics will continue to shape technological, scientific, and philosophical advancements. From renewable energy to quantum computing, thermodynamics provides a crucial framework for understanding how energy interacts with matter in every field. In the quest for more efficient, sustainable technologies, the principles that govern energy transformation will remain at the heart of our pursuit to solve some of the most pressing challenges of the 21st century.